Good morning, dear students. Today we have to start by the activity 5, the first part of the activity 5 about the nature of nervous message recordable electric signals. At the end of this video, you will be able to recognize the devices used to identify the nature of the nervous message and to explain the existence of resting potential. When we touch a hot object, what do we do? What is the pathway of the nervous message in this case? We know that the pathway starts by the stimulus, then the sensory organ, the central nervous system, effector organ, and to apply the action. What is the stimulus here when we touch a hot object? So the stimulus, the cause to make the action is the hot object. The sensory organ that detects the stimulus is the skin of the hand. The central nervous system is the brain or the spinal cord. The effector organ is the muscles of the hand because we have to remove the hand directly, which is the action. What transmits the nervous messages? From the sensory organ to the central nervous system is the sensory nerve. From the central nervous system to the effector organ is the motor nerve. So we have a message which is transmitted to the central nervous system and another one from the central nervous system. So what is the nature of this nervous message? Can we see it? Can we feel it? How can we record this nervous message? Many instruments can be used to record a nervous message, like the case or the oscilloscope, which allows us to observe the obtained recording, and the voltmeter, which will give the value of the voltage. Since the nervous message is recorded by the oscilloscope or the voltmeter, so it's not chemical, it's electric. Your neurons carry messages in the form of electrical signals called nerve impulse. To create a nerve impulse, your neurons have to be excited by a stimulus. When neurons are excited, a nerve message is created in the form of electrical signals. So the nature of the nervous message is electric. A nerve fiber may be transmitting or not transmitting messages. So when the nerve fiber is not transmitting messages, we have no stimulation, the nerve fiber is at rest, so we are talking here about resting potential. When the nerve fiber is not transmitting messages, it is at rest. What is the value of resting potential? So, first of all, the word potential difference, or PD, is the difference of distribution of ions between inside and outside the axon. So the word potential difference, like we studied it in physics. To be able to measure the potential difference, observe with the figure. So we have to measure the potential difference in an axon. Okay, we have to insert one electrode inside the axon and another one outside the axon. If we insert both electrodes in the same medium, so the result will be 0 because it's the difference between 2 points in the same medium is always 0. The voltmeter gave us minus 70 millivolt. This neuron is at rest, so this value corresponds to resting potential. First, do not forget that a nerve fiber or the axon is a part of the cytoplasm of a neuron. So when we apply the experiment, the nerve fiber should be in a physiological liquid. It's a water-based liquid that contains ions and cells essential to body functions to stay alive. So the obtained value of resting potential is minus 70 millivolt recorded by the voltmeter. But how did we obtain this value despite the absence of a nervous message? This axon is at rest, so it should give 0. Why? It will give minus 70 millivolt. So let's watch the video.
The human brain alone contains about 100 billion nerve cells, called neurons. A neuron, like every other cell, has positively and negatively charged ions, inside and outside. Further, A resting neuron has a greater negative charge on the inside surface of the plasma membrane and a greater positive charge on the outside surface. This partitioning of charge creates a voltage difference across the membrane known as the resting membrane potential, which can be measured using a voltmeter. On average, an intracellular electrode records a value of minus 70 millivolts. The resting membrane potential depends on two factors. First, it depends on the presence of sodium and potassium gradients across the plasma membrane. Specifically, there are more sodium ions outside the neuron than inside, and more potassium ions inside the neuron than outside. Second, the resting membrane potential depends on the differential permeability of the plasma membrane to sodium and potassium ions. Leak channels in the plasma membrane allow sodium and potassium ions to diffuse or leak down their concentration gradients. The membrane contains many more potassium leak channels than sodium leak channels. Thus, the membrane is much more permeable, or leaky, to potassium ions. As positively charged potassium ions leak out of the neuron, the inside surface of the membrane becomes negatively charged compared to the outside surface.
So, observe well this figure. It's an axon. This is the inside of the axon and this is outside. We have many ions like sodium ions, potassium ions, Cl- and A-. We have to insist only on sodium and potassium ions. Where do an A+ ions dominate? In which medium? So, inside the cell we have 15 millimole and outside 150 millimole. So, sodium ions dominate in the extracellular medium outside the cell. Where do potassium ions dominate? Inside the cell we have 150 and outside we have 5 millimole. So, potassium ions dominate inside the cell. So, the first origin of resting potential is the unequal distribution of ions, because the distribution of ions between intra and extracellular medium is not the same. Sodium ions dominate outside the cell while potassium ions dominate inside the cell. Another origin of resting potential, observe well the following figure. The circles are for sodium ions and the squares or the rhombus for potassium ions. As we notice that sodium ions dominate in the extracellular medium and potassium in the intracellular medium. The dark purple are for potassium channels while the light one for sodium channels. Observe well, this is for potassium, 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 potassium. We have 4 channels for potassium while only 1 channel for sodium. So the potassium ions can diffuse, can move more than sodium ions because the number of channels for potassium is greater than that of sodium. So the second origin of resting potential is, since we have more potassium channels than sodium channels, so the diffusion of potassium outside is more than diffusion of sodium inside, since potassium will move outside the cell because we have more potassium ions inside than outside, while we have more sodium ions outside than inside. Always the diffusion is from the higher concentration to the lower concentration. So outside will become more positive. So as a summary for the resting potential, we have 2 causes, 2 origins. The first one is the unequal distribution of ions. Sodium dominate outside the cell while potassium ions inside the cell. And the second one is the selective and differential permeability. Selective because we have channels only for sodium and potassium ions, while these channels are different. The number of potassium channels is more than that of sodium channels. These 2 causes create the resting potential of minus 70 millivolts. As an evaluation, we have to choose the correct answer. What is the nature of the nervous message? Is it chemical, electromagnetic, or electric? So it's an electric message. The second one, the value of resting potential is 0 millivolt, 100 or minus 70 millivolt. It's minus 70 millivolt. Sodium ions dominate in extracellular, intracellular, or in both media. Sodium dominate in the extracellular medium. For the next time, you have to study the summary sheet part 1.